Okay, so welcome everyone. And today it's our great pleasure to have Evgeni Dimitrov, who will be telling us about towards universality for Gibbsian line ensembles.
So thank you very much for the introduction. It's certainly a great pleasure to be giving this talk. So today I will discuss a certain framework that I have been developing over the last few years that can be used to prove KP's universality for Gibbsian line ensembles. So I'll begin my talk by kind of telling you what are Gibbsian line ensembles. So I'll give you a few examples of such objects. I'll then formulate the framework that I'll be using to study these things. So parts of the framework are completed and parts are still under construction. And so I'll tell you kind of what is the progress towards applying this framework to two types of models. So one is of random plane partitions and one is of the low gamma polymer. And then in the end, if I have some time, I'll finish with some remarks. So first of all, what is a line ensemble? So a line ensemble is just a collection of random continuous functions. So these functions are all defined on the same probability space, and they are indexed by some index capital sigma. So in this talk, this capital sigma will be just some collection of consecutive integers starting from 1, which could be finite or infinite. And so a line ensemble is just either a finite or a countably infinite collection of random functions on the same probability space. And just as a simple example, we can consider the case when sigma is equal to the set 1, 2, 3. And let's say we have an interval lambda 0, 1, and then a line ensemble, an example of a line ensemble is just take 3 independent standard Brownian motions on the interval 0, 1. This is what I would like to call a continuous line ensemble, to emphasize the fact that the underlying path measure is given by a Brownian motion or a Brownian bridge or something like that. Now, line ensembles come in many different forms. So let me give you an example of a discrete line ensemble. Here I'm going to consider kind of the model of lozenge tilings of a polygon. So what I have here is a certain polygon that's drawn in the triangular array. And I'm going to consider all possible tilings of this model by these 3 tiles. So here is one possible tiling. There's many others, and I'm going to put the uniform measure on all such tilings. Now, to get to a line ensemble from this picture, all you need to do is you need to perform a simple affine transformation that gets you to this thing here. And then you can draw kind of small segments, black segments that connect the midpoints of the blue and the red parallelograms in this picture. And this way, you obtain a random collection of upright paths. So here I just have the same paths, but shifted a little bit. And so this is an example of a discrete line ensemble. Okay, so the next thing is, what is a Gibbsian line ensemble? And sort of in vague terms, a Gibbsian line ensemble is just a collection of labeled random walks or Brownian motions whose consecutively labeled curves interact locally. So there's many different ways that these curves can interact locally. So I'll just give you a couple of examples to illustrate what I mean by this local interaction. So this is an example of a Gibbs property for a continuous line ensemble. It's called the partial Brownian Gibbs property. And we say that the line ensemble satisfies this property if it satisfies 2 conditions. So the first condition is that the curves need to be strictly ordered. So the L1 needs to be somehow on the top, then L2 needs to be strictly below that, L3 is below that, and so on. Okay, so the second condition is more complicated. And what it says is that the local distribution of your curves is that of avoiding Brownian bridges. And one way to interpret this condition is that the law of your line ensemble is invariant with respect to the following resampling procedure. So what you do to resample this line ensemble is you fix 2 times little a and little b. And then what you're going to do is you're going to sample your line ensemble and then erase the middle part. So if you erase the middle part, this is what you'll get. And then what you do is you fill in the gaps. So you basically sample independent Brownian bridges that interpolate between the red dots that are independent but conditional on avoiding each other and also avoiding the k plus first curve. And in this way, you obtain a new line ensemble. And the essence of the partial Brownian Gibbs property is that the new ensemble has the same law as the old one. So it's invariant with respect to this resample. Now, let me tell you something about this word partial here. So in this definition, the bottommost curve, the nth curve, plays a special role. So it could be deterministic, it could be something else. So it's not allowed to be resampled. So it plays the role of a bottom boundary for a line ensemble. Now, if you have infinitely many lines, meaning there is no bottommost curve, or if there's finitely many lines, but the resampling also extends to the bottom guy, then you drop the word partial and you arrive at what's called the Brownian Gibbs property. And this is a term that was coined by Corwin and Hammond in 2014. Okay, so this is kind of a continuous Gibbsian line ensemble. And the discrete analog of this is formulated in this slide. So basically, we say that a line ensemble satisfies, so in the discrete case, we call it the Schur-Gibbs property. So the name Schur comes from the Schur symmetric functions. If it basically satisfies the analogs of what was in the previous slide. So basically, you want the curves to be ordered. And also the local distribution of this now discrete line ensemble needs to be that of avoiding Bernoulli random walkers. So if you replace avoiding Brownian bridges with Bernoulli random walk bridges, then you arrive at an analogous definition for the discrete set. And it takes maybe a couple of minutes to realize that if you look at this tiling model and you put the uniform measure on all possible tiles, you exactly, and you interpret that in terms of the lines, and then the induced laws on the lines is that of the uniform measure on all upright paths that need to start at these consecutive locations, and they need to terminate at these consecutive locations, and are uniform conditioned to avoiding each other and also avoiding this bottommost boundary here. Okay, so these are kind of examples of Gibbsian line ensembles, and the questions that I'll be interested in understanding is what are their scaling limits? So scaling limits of line ensembles kind of naturally split into two categories. One is if you, and this is the one that's discussed in this slide, is when the number of lines is fixed. So what you're going to do is you're going to look at one such ensemble, and you're going to run it for a long time. But the number of lines is fixed. It's some finite number. In this case, it's 3. And then you're interested, what are the scaling limits of these lines? And so it takes a little bit of time to realize, but essentially the only sensible thing to do is that you need to rescale the starting locations of these lines by square root of t. And under the scaling, you need to have something either deterministic or random, some xi's. And also the terminal points, the y's under square root of t scaling need to converge to some either deterministic or random y's, except that maybe you need to subtract some global slope that you have in your model. And if this is the case, then the entire line ensemble is going to converge if you spatially rescale it by t and vertically rescale it by square root of t, or again, you need to subtract this global slope. And in fact, it's going to converge to nothing but the finitely many Brownian bridges between the x and the y's that are, again, conditioned on avoiding each other. So this is this type of scaling where you rescale horizontally by t and vertically by square root of t means that this model this limit belongs to the Gaussian universality class that is marked by these scaling exponents of 1 and 1/2. And here I just recall the classical statement from probability theory called Donskoy's theorem that says that the random walk converges to Brownian motion. And what you see is that the scaling that we're performing here is the same as the scaling that we have for the line ensemble. So basically, you just obtain somehow a multi-level version of Donskoy's theorem. Now, a more interesting and harder to understand question is understanding the scaling limits of line ensembles when the number of lines increases together with time. And just for simplicity, I'm going to assume that time is equal to the number of lines. And to understand what is happening, I'm going to focus on a particular model, that is Dyson-Brownian motion. So Dyson-Brownian motion is just a collection of n Brownian motions that are all started from the origin and are conditioned to never cross each other for all positive time. So I'm going to start Dyson-Brownian motion with n Brownian motions, and then I'm going to look at a time horizon n. And I'm interested in what is happening, or how do I need to scale the edge of this line ensemble to get a non-trivial limit. Now, because the paths are conditioned on avoiding, they are going to repel each other. So that is going to shift the edge of this ensemble deterministically by order n. So in order to get a non-trivial limit, we need to shift by some constant times n. In addition, you will again have a local slope in the model that you need to subtract here. And then you need to horizontally rescale now by n to the 2/3 and vertically by n to the 1/3 in order to get a non-trivial limit. And in fact, for Dyson-Brownian motion, this limit is known, and it's one of the fundamental scaling limits in the KP's universality class. It's called the Parabolicary line ensemble. So let me explain in words the possible point of confusion in this picture. So this parallelogram does not take into account the fact that we're subtracting the slope. When you subtract the slope, it's going to become a rectangle, and only afterwards do you kind of rescale horizontally by n to the 2/3 and vertically by n to the 1/3. I couldn't quite figure out how to draw it well, but hopefully the words that I said explain what's going on. So this Parabolicary line ensemble, probably people have heard about its cousin, the area line ensemble. So the relationship between the two is very simple. It's encoded in this equation. So the area line ensemble, it's a stationary line ensemble with infinitely many lines. It has the area process sitting on the top, and the 1-point marginals of the area process are the GUE Tracy-Whittem distributions from random matrix theory. The parabolic one is basically the same, except that you need to subtract the parabola and multiply by 2 to the -1/2. Now, when you subtract this parabola, the resulting line ensemble globally looks like an inverted parabola. And the benefit of working with that object is that it has the Brownian Gibbs property from a few slides ago. And this additional 2 to the 1/2 is just put in there so that the diffusion parameters underlying this Gibbsian line ensemble for the Brownian motions all have diffusion parameter 1. Now, if you have never seen these objects, these area processes or area line ensembles, the key takeaway points here are that as you increase the number of lines together with time, you leave the Gaussian universality class and you enter a new universality class called the KPZ universality class. This new class comes with different scaling exponents, whereas before we rescaled horizontally by t and vertically by square root of t. Here we horizontally need to rescale by t to the 2/3 and vertically by t to the 1/3. So the scaling exponents are different. And also the limiting objects are different. So before they were Brownian motion or Brownian bridges, now or they're multi-line analogs, now they're going to become the area process or its multi-line analog. Okay, so in this slide, I made an implicit claim that the Parabolicary line ensemble is a universal scaling limit. So let me bolster it with a few additional examples for which this type of convergence is known. So here I just drew different types of statistical mechanics models that naturally carry a structure of a line ensemble and for which convergence to the parabolic area line ensemble is known. One such model is given by uniform domino tilings of the Aztec diamond. Another one is given by the multi-layer polynuclear growth model. And here we again have the lozenge tiling model for a certain polygon or class of polygons, where again you've already performed some sort of an affine transformation to make it look nicer. So for all of these models, it is not, again, they have naturally a structure of a line ensemble, and they converge and they're known to converge in the finite dimensional sense to the parabolic area line ensemble. Now, the reason this thing is known for these models is because all of them have the structure of what's called a determinantal point process. So I'm not going to assume that people know what the determinantal point process is. The key point here is that the correlation functions for each of these models can be expressed as determinants of what's called a correlation function or a correlation kernel. And this is just a function of two variables. And if you can find nice expressions for this correlation kernel, and you can show that in a sufficiently strong sense it converges to the area kernel, which is the kernel underlying the finite dimensional distributions of this parabolic area line ensemble, then this would be enough to conclude this finite dimensional convergence. Now, most models don't have this determinantal point process structure. So even nice integrable models don't necessarily have it. Yet we're still interested in establishing either this or stronger notions of convergence to the parabolic area line ensemble. And so the methods that were used in these types of models become inapplicable. So in order to kind of overcome this issue, I have been trying to come up with a framework that can be used, at least for some class of models, to show convergence to the parabolic area line ensemble. And here I'm already going to ask a more ambitious question, not just finite dimensional convergence, but kind of convergence in the topology of uniform convergence over compacts, which is a stronger than finite dimensional convergence. So this framework consists of three parts. So the first part, in order to show that some sequence of line ensembles converges to the right objects, you want to maybe first of all show that that sequence is tight, so that you have some subsequential limits. And then you also want to show that all subsequential limits satisfy the Brownian Gibbs property that the limiting object has. So typically the objects that we work with are already kind of discrete Gibbsian line ensembles. So they have a discrete Gibbs property that formally limits to the Brownian Gibbs property. So this is why we kind of suspect this thing to be doable. The second point is you still want to kind of prove something quantitative. So you want to show that the top curve of your discrete line ensemble converges in the finite dimensional sense to the top curve of the Parabolicary line ensemble, which is called the Parabolicary process. And then the third step is to basically show that these two conditions that you know all your subsequential limits have. So if you manage to prove condition 1 and 2, then what you would know is that any subsequential limit has the Brownian Gibbs property. And also you would know that its top curve is the Parabolicary process. And then the third point is to show that those two conditions uniquely pinpoint the possible subsequential limits, meaning that all subsequential limits need to be the same and they need to match the Parabolicary line ensemble. Well, the main advantage of this framework is that it reduces the amount of quantitative information you need to control for your discrete line ensembles from the full ensemble to just the top curve. Okay, so we don't care if we have formulas for the second, third, or so on curves. So that's what we're trying to overcome, the necessity for such formulas. So I'm going to explain each one of these points in this talk. So I'm going to start with the third one. And this brings us naturally to the problem that I like to call the princess and the pea. So the setup is as follows. So you have two beds. One of them has a perfectly flat base, and the other one has an almost flat base, except that it has a small aberration, aka the P. Now you start piling a bunch of matrices on top of these two beds, and you can put different number of matrices, and they can have random or deterministic endpoints. And then the only thing you demand is that the distribution of these matrices is conditional on the red dots, is that they need to be avoiding Brownian bridges that also avoid each other, but also the base, or in this case, the base and the P. Now a keen observer, aka the princess, observes both of these line ensembles. So she sits on both of the beds, but she only feels the top matrix of each of the beds. She doesn't really feel any of the bottom ones, but she's very sensitive. So by simply sitting on the bed, she can determine everything there is to know about the top curve. And then the question is, can the princess, based on this information from just the top curve, determine whether there is or there isn't a P at the bottom of the bed? And the answer is yes. And in fact, she can determine much more than this. Now, by simply observing the top curves of these ensembles, she can determine the entire distribution of the full ensemble. And in particular, she can see if the bottom one has a P or not. So this is a theorem. It's a result by myself and Konstantin Matietsky from last year. So the statement is as follows. Suppose you have two line ensembles, L1 and L2, and they both satisfy the Brownian Gibbs property. And in addition, suppose that the top curve of the first ensemble has the same finite dimensional distributions as the top curve of the second ensemble. Then the conclusion is that the full ensemble laws need to match. Okay, so in plain words, what the theorem says is that a Brownian Gibbsian line ensemble is completely characterized by its top curve. So unless I have some time at the end, I will not go into the proof, but what I want to mention is that the proof is non-constructive. So even if you give me a Gibbsian line ensemble and nice formulas for the top curve, I cannot tell you what the distribution of the second one is. I know there is a unique possible second curve distribution that can work, but I don't have a way to give you formulas back. So this, the last thing I'll mention here is that this theorem answers the third part of the framework, because it pinpoints the Parabolicary line ensemble as the unique line ensemble that has the Brownian Gibbs property and the Parabolicary process on the top. So before we go back to the framework, what I want to do is I want to give you kind of a positive temperature analog of this theorem that was established more recently. So let me kind of try to formulate a more general type of continuous Gibbsian line ensemble.
Wait, so can I ask a question before you
yeah,
go on?
sure.
When you said the top one here, I just got confused. Is that the one that you're not? Is that like the fixed one, the free one that you're not allowed to condition on?
The one that is fixed is the bottom one. The base of the bed is the fixed one. That the one on the top is the fluctuating one.
Okay.
So
that one is conditionally Brownian given the bottom.
Yeah.
Okay.
You need at least one of them to be Brownian. And you start from the top and work your way down. That's how it works. Right. Any other questions? Okay, so let's try to digest what's on this slide. So I'm going to define what's called the H-Brownian-Gibbs property. So we say that the line ensemble has this property if the conditional law of k consecutive curves in this ensemble is the law of k independent bridges that have been reweighed by the following Radon-Nikodym derivative. So okay, so this is not a complicated function, but if you haven't seen it, it might not be easy to digest. So the point, so first of all, the interaction between these curves is reflected by this function h, which I like to call the interaction Hamiltonian. And so the argument of h is the difference of two consecutively labeled curves. So in this way, the only adjacent curves in the index interact with each other. So if the distance in the index is more than 2, the curves don't talk to each other, so only neighboring curves interact with each other. In addition, the argument here being the same means that the interaction is also spatially local. And the way that these curves interact is basically through an energetic penalty that is reflected in the distribution. So basically, if a certain path configuration results in a high h, then that path configuration is penalized exponentially. And so the curves are basically independent bridges, but they like to align themselves around the path configurations that minimize the h. So this is the usual sort of positive temperature Gibbsian property that people consider. And just to relate it to the one that we did discuss, the Brownian-Gibbs property, it arises from this type of a formulation if you pick h to be the function that is infinity for positive values of x and 0 otherwise. So what happens if the argument here is positive? So if the argument here is positive, it means that the I plus first curve overcame the ith one, so the paths went out of order, and any such path configuration gets a weight of e to the minus infinity, so that's 0. Now, if the paths do stay in order, then all of these h's become 0, so you're weighing by e to the 0. And of course, if you're weighing by e to the 0, you get the same distribution back. So this is how you recover the usual Brownian-Gibbs property from this formulation. Now, there is another natural choice for h that people have considered, which is e to the some constant, positive constant t times x. So and there is an actual line ensemble that satisfies this Gibbs property. It's called with this interaction Hamiltonian. It is called the KPZ line ensemble, and it was introduced by Corwin and Ham. So what I want to kind of mention here is that this family of interaction Hamiltonians, as t varies from 0 to infinity, interpolates between complete disorder and complete order. So if t is equal to 0, this Hamiltonian is going to be just 1, so it's going to be constant. And so this Radon-Nikodym derivative is also going to be constant. Now, if you reweigh a measure by a constant Radon-Nikodym derivative, the measure doesn't change. It stays the same. And so the local distribution will be just independent Brownian bridges. They can fluctuate however they please. Now, as t tends to infinity, this function will exactly converge to the function that we had here, this underlying the Brownian-Gibbs property. And that one demanded that all the paths are strictly ordered. So as t varies from 0 to infinity, you go from complete disorder to complete ordering of the curves. So as I mentioned here, there is an actual line ensemble that has this interaction Hamiltonian. And I'll just explain kind of what are the differences between this ensemble and the Parabolicary line. So this one also globally looks like an inverted parabola. However, one difference is that the paths are no longer strictly ordered. So they can go out of order. However, every time they go out of order, they get some sort of an exponential penalty, energetic penalty. So even though they're allowed to, and they do every once in a while, they tend to stay in order whenever they can. In addition, in the Parabolicary line ensemble, the top curve played a distinguished role. It was the Parabolicary process. And here again, the lowest indexed curve, L1, it plays a special role. It's the solution to the KPZ equation started from narrow edge initial data. Okay, so a natural thing to try to do is basically classify the KPZ line ensemble by exactly these two conditions: the H-Brownian-Gibbs property and the KPZ equation being the lowest index curve. And that's a theorem now. It's a result from earlier this year. So the statement is that suppose you have two line ensembles, L1 and L2, and they both satisfy the H Brownian Gibbs property, where the H, I'll say in a moment what it can be. And suppose in addition that the top curves have the same finite dimensional distributions for these two ensembles, then again, the full ensembles need to match. Now, this is going to be true if you make certain assumptions on the function H, on this interaction Hamiltonian. So one of these assumptions is that the H needs to be convex. And the second condition here is a certain sort of quantified statement that this function needs to grow like an exponential function near infinity. So for some positive lambda here. So in particular, if H is equal to e to the lambda x, this ratio is going to be identically equal to this e to the lambda x. And so this difference is going to be identically equal to 0. But by having such a statement, we can handle more complicated interaction Hamiltonians than just the exponential. Again, in simple words, what the theorem says is that the H Brownian, an H Brownian Gibbsian line ensemble is completely characterized by its lowest indexed curve. And in particular, the KPZ line ensemble is the unique line ensemble that has this interaction Hamiltonian and has the narrow wedge solution to the KPZ equation at the top. Okay, so this is the end of the detour. We're going to go back to the framework. So this third point was the theorem from 3 slides ago. So we've resolved the third point. The next thing I'll discuss is the first point here. So how do you show that the sequence of line ensembles is tight? And so I'm going to explain what is kind of the progress in towards establishing tightness for 2 types of models. And for each one of them, I will formulate a statement that looks like this. So you'll be given some sequence of discrete line ensembles. And what you will have as an assumption is that the 1-point marginals of these of the top curve of these ensembles is tight under suitable shifts in scales. And then the conclusion would be that under the same shift in scales, the entire top curve is tight. So kind of 1-point tightness together with the Gibbs property implies tightness of the entire top curve. Now, this is not the same as what we have here, because in order for point 1 to work, we need the full ensemble to be tight, not just the top curve. So that's why it's partial progress. But in the end, I'll mention some more recent work that that manages to establish tightness, at least for some special choices of parameters. Okay, so let me define for you first the log gamma polymer. So the log gamma polymer is built from an infinite array of inverse gamma random variables. So these random variables, they depend on a positive parameter theta, and they have some density. There's positive random variables. It's not important what this density is, but I wrote it down just in case we're interested. So from these weights, what we're gonna, or from these IID variables, we're gonna build a partition function. So how do you do that? So you first consider all possible upright paths that connect the point 1, 1 to the point little n capital N. So these paths, they follow adjacent sites on the integer lattice, always going to the right or up. Okay, so for each such path, you can define its path weight. So the path weight is nothing but the product of the vertex weights that lie inside of these integer sites. And then the partition function for this model, the point-to-point partition function, is just the sum of the path weights over all possible paths that start from 1, 1, and then at little n capital N. And if you take the logarithm of the partition function, you obtain what's called the free energy, or the point-to-point free energy for this polymer model. And this is the way to think about this is a function of little n. So for each little n, and little n is 1, 2, 3, 4, 5, and so on, I can compute this quantity. And it's going to be some random number. And then I'm going to plot it here. And then for good measure, I'm going to linearly interpolate these points. And in this way, I obtain a random continuous function. Now, what's remarkable about this model is that this random continuous function embeds as the lowest index curve of a line ensemble that has a nice Gibbs property. So I'll explain in the next slide what I mean by nice. But what I want to mention here is that this is a result of a very nice paper by Corwin, O'Connell, Shepalainen, and Zigouras, and it's a consequence of applying the RSK, the geometric RSK correspondence to this array of IID inverse gammas. Now, if you start with a different distribution that's not the inverse gammas and you apply this RSK, you will again obtain some sort of a line ensemble if you apply the same type of procedure, but it will no longer have a nice Gibbs property. Okay, so the fact that this thing locally has a nice structure is a consequence of having inverse gamma weight. So that is a very special property. Let me kind of give you some flavor of what this ensemble looks like. So I'm not going to define it for you. It's a little bit too complicated to do that in a short amount of time. But what I want to mention is that the lowest index curve is just the point-to-point partition, free energy of the polymer model. Now the other curves in this ensemble are also related to free energies, but from higher rank partition functions. So the point here is that they have some physical meaning related to the polymer. They're not just some abstract construction that doesn't make any sense. They have some physical meaning. And then the Gibbs property is basically encoded in this local distribution of the curve. So you should not try to read this very carefully. Let me try to guide you through it. So the local distribution of k consecutive curves in this ensemble is proportional to the product of two terms. Now, the first term, what it is saying is that the evolution of the L's is that of independent random walkers that have log gamma jumps. So the jumps of these random walkers are log gamma distributed. And the second term here is basically encoding a local interaction between consecutively labeled curves that is very similar to what we had for the KPZ line ensemble. So in particular, the interaction Hamiltonian here is again going to be an exponential like it was for the KPZ line ensemble. And again, the interaction is only for adjacent curves and locally in space. So there's a kind of a discrete shifting by one, which you should ignore. So here I just recalled the Radon-Nikodym derivative that we had before. So the difference is basically that here, for the H. Brownian Gibbs property, the underlying path measure was that of independent Brownian bridges, and in the discrete model, they get replaced by log gamma random walk bridges, but the interaction Hamiltonian is basically the same. So you should really think of this line ensemble as an integrable discretization of the KPZ line ensemble. So at this point, you can look at this structure and just forget about the polymer model if you want, and just consider a generic collection of random walkers with not necessarily log gamma distributions, but other possible jumps. And here, maybe not just exponential interactions, but other types of interactions. And you can ask, can you show tightness for these types of line ensembles? And under what conditions can you do it? And so this is kind of the theorem that we established with Guillaume Barracand and Ivan Corwin again earlier this year. So we consider kind of general HRW. So again, these are line ensembles that are built from some generic random walks that have some generic type of interaction. And what we were able to show is that if you know that the 1-point marginals of the top curve or the lowest index curve are tight under suitable shifts and scales, then the entire line, the top curve of this ensemble needs to be tight under the same shifts and scales. So there's some certain technical conditions on H and HRW, so you need them to be convex, things like that, that I'm not going to go into. But this is somehow a general framework for establishing tightness, right? So we kind of dropped the integrability of the log gamma polymer when we proved something for more general random walkers and interactions. Again, in simple words, what the theorem says is that if you have 1-point tightness plus a Gibbs property, that implies tightness of the whole first curve. And for the log gamma polymer, it satisfies the conditions that we need as input for this theorem, because we not only do we know that the 1-point marginals are tight, we know that they converge to the Tracy-Whittam distribution. So this result was established first by Borden, Corwin, and Remenick. So I remind you that the whole model depended on a positive parameter theta. And when theta is small, is small enough, it was shown in this paper. For any value of theta, but kind of only for slope 1, this convergence to the Tracy-Whittam distribution was established by Christian and Castell. And last year we did it with Barracand and Corwin kind of for arbitrary slopes and parameters theta. Again, I will not really go into the proof, but what I want to do is I want to mention one key ingredient that goes into the proof, and this is a result by myself and Xuan Wu. So the statement here is you have just a random walker, and you consider its conditional distribution, conditioned on it being equal to z at time n. So in this way, you obtain what I call a random walk bridge. So then the statement of this theorem is that under certain conditions on the jumps, this random walk bridge can be strongly coupled to a Brownian bridge of appropriate variance, in the sense that if you look at the soup distance between these two objects, then the probability that this soup distance is bigger than logarithmic in scale is exponentially small. So this is a type of KMT type coupling for bridges. And the way that this type of a result is useful for establishing tightness, so I'm not going to assume that people know anything about proving tightness for line ensembles, but you know, at some point when you're dealing with random functions and you want to show that they're tight, you need to get some control on the modulus of continuity of these curves. And this type of statement becomes indispensable because underlying these line ensembles, typically we have some random walker that using this theorem, we can very well compare to a Brownian bridge. And for Brownian bridges, we know a lot of information. We have all sorts of control on its modulus of continuity, so we can translate these types of statements that we know for Brownian bridges. We can translate them to random walk bridges and get a handle on a lot of things. Okay, so at this point, you can completely forget about the low gamma polymer. In the rest of the talk, I'll focus on one other model, which is that of random plane partitions. So first of all, what is a plane partition? So we have two natural numbers, capital M and capital N, and then we're going to consider an n by m array, and we're going to fill it with non-negative integers that weakly decrease along rows and columns. So there is a natural geometric interpretation of this object, which is drawn here. So basically for every site, you put this many unit cubes on top of each other. So this 3 ones that you have here, for example, correspond to these 3 stacks of 1 cube. And these 3 3s correspond to these 3 stacks of 3 cubes. Hopefully it's clear from the picture how these two things correspond to each other. And what we're going to do is we're going to put a probability measure on the collection of plane partitions that have their base in this n by n box. So this measure is going to depend on 2 parameters, little a and little t, that are both between 0 and 1. Probability of a plane partition is going to be up to a normalization constant, the product of 2 terms. So the first one is just a to the diagonal of pi. So the diagonal of pi is exactly what you think it is. You just go over the main diagonal and you sum up all the entries. So the way that you should think about this term is that it's a volume constraint for the plane partition, because it's preventing the diagonal from becoming very high. But of course, if the entries are weakly decreasing along rows and columns, having a small diagonal means that all the entries need to be small. Now, the second factor here is going to depend only on the parameter little t, and it's going to be a polynomial in t. It's a product of simple factors that are 1 minus t, 1 minus t squared, 1 minus t cubed, and this factor reflects the geometry of the plane partition. And so I'm just going to explain using the picture how you write down this polynomial. So what we're going to do is we're going to look at the balconies, kind of the level, the flat level planes that you have in your plane partition, and these correspond to connected components of cells that you have in the array that have the same entry. So here I have a big C of 3s, and these correspond to this big balcony here. Now for each cell on a balcony, I'm going to color it. I'm going to assign it a level, and this level is measuring the diagonal distance from the cell to the boundary of the balcony. So all of these cells are unit distance away diagonally from the boundary. This one is 2 units away, so it gets level 2, and this one is diagonally 3 units away, so it gets a level 3. And when you do this coloring, you obtain connected components of the same level. And for each connected component of the same level, you're going to get a factor that is reflecting the level of that component. So for example, I have a single connected component of level 3. And so that produces this factor of 1 minus t cubed. The 3 is reflecting the level. I have 3 connected components of level 2. So I get 3 factors of this 1 minus t squared. And then I have 7 connected components of level 1 that produces this factor here. So it's not particularly important what this polynomial is. The point is that it is a simple polynomial in t that reflects the geometry. And if I gave you a plane partition, you can just do the coloring and tell me exactly what this polynomial is. Now, this model was initially studied by Mirjana Vuletic in 2009. And you might think that this is kind of an exotic model from the way that it's described, but it's actually very well connected to many known objects. So one connection is that this is a special case of what are called the ascending McDonald processes that were introduced by Corwin and Borden. Another reason that you might be interested in studying this model is that it naturally has the structure of a Gibbsian line ensemble. So let me explain to you how that arises. So what you're going to do is you're just going to look at the level lines of your plane partition, and then you're going to, kind of rotate the picture a little bit so that you get kind of upright paths like the one I have drawn here. What is the Gibbs property? So if you take the geometric interpretation that they gave you on the previous slide and interpret it in terms of the lines, basically what you get is the following Gibbs property. So I'm just going to explain it for the second, using the second curve condition. So I'm going to fix the first and third curve and tell you what the conditional distribution of the second one is, but the same works for the other lines as well. So the conditional distribution of the second curve given the first and the third one is basically going to be uniform on all upright paths that connect its endpoints, and also stays in order relative to L1 and L3, except that you're going to perturb it. You're going to perturb this uniform distribution by multiplying the weight by some factors that involve 1 minus t to some power. So what are these powers? So basically, every time two of these lines come close to each other, so here the distance goes down from 3 to 2, that produces a factor of 1 minus t to the distance, which is 1 minus t cubed. Here the distance went down from between the second and the third went down from 2 to 1, and that produces this factor, 1 minus t squared. And here it went down from 1 to 0, so that produces this factor of 1 minus t. So if t is equal to 0, of course, all of these factors are going to be just ones, and you recover precisely what we used to call the sure Gibbs property. This one, because it has a general t, from the symmetric function part of things, we call it the Hall-Littlewood Gibbs property. But the way that you should think about this Gibbs property is it's some sort of a quantization of the uniform measure on avoiding paths, with some quantization parameter little t. Now, another reason that you might want to study this model, even if you're not big on Gibbsian line ensembles, is that this model is actually connected to what's called the stochastic six-vertex model. So basically, if you look at the red curve here and you reflect it and shift it by some deterministic number, then that random curve has the same finite dimensional distribution as the height function for the stochastic six-vertex model. So if you want, this model gives you a natural way to embed the height function of the six-vertex model into a Gibbsian line ensemble. And by the way, this distributional equality was discovered by Borden, Buffetov, and Wheeler. Okay, so for this model, we have an analogous statement like the one we did for the low gamma polymer. So if you have a sequence of Hall-Littlewood now Gibbsian line ensembles, and you know that the top curve of these ensembles has 1 point tight marginals, then in fact the entire top curve needs to be tight under the same type of scaling. So this is an old result by myself and Ivan Corwin. And so more recently, during a summer RU project last summer, we wanted to kind of lift this result to the full line ensemble, but because it's a summer project, we wanted to do it in something manageable. And so we only consider the t equals to 0 case. So again, t equals to 0 means that you're basically looking at a collection of avoiding Bernoulli random walkers that are started from some random and ended some random positions. And what we were able to show is that if you have 1 point tightness of the top curve, then in fact the full ensemble needs to be tight. And moreover, any subsequential limit satisfies the Gibbs property, the Brownian Gibbs property that we had from before. So this thing resolves, at least when t is equal to 0, this question, the first part of the framework. Now, there's still more work to be done for general t, but at least now we have some progress towards getting there. So the last thing that I'll mention, and I'll be brief, is about the second point here, which is finite dimensional convergence of the top curve to the Parabolicary process. So for the Hall-Littlewood line ensembles related to the plane partitions, there is this partial progress in this direction. So again, don't read the statement. Let me read it for you. So what we're doing is we're considering a collection of random line ensembles that are coming from the plane partition model. And then I'm going to fix 2 times little s1 and little s2 in R. And from these, I'm going to build discrete times, little n1 and little n2. And these are basically take the s's and scale them under the KPZ scaling to what these things should be in the discrete world. Basically, shift by a big number times n plus s1 times n to the 2. And then what we're going to do is we're going to look at the top curve at these two times, little n1 and little n2. And of course, we always need to, subtract the appropriate thing and appropriately rescale. It's not important what these constants are. And in this way, we obtain these two variables are measuring the joint distribution of the top curve at two times. And what we were able to do is we were able to prove that these two random variables jointly converge to the Airy process at times little tau1 and tau2 that are related to the s's by a simple rescaling. So basically, they're equal to the s's times a constant. Okay, so at the time that this result came out, it was the first rigorous multi-point result for a non-determinantal model. So the Hall-Littlewood is not a determinantal point process. And this was kind of the first case that we were able to show more than 1 point convergence for such models. There were previous works, non-rigorous works based on replica approaches in the physics literature. So there's several people here, Dutsenko, Prolak, and Spahn, Imamura, and Sasimoto. There's others. On the math side, there was also kind of a partial progress towards understanding this question for the low gamma polymer. And this is in a paper by Nguyen and Ziguras. Now, they kind of got nice formulas, but ultimately were not able to push the asymptotic analysis through. And here we were able to do it, but kind of under some restriction on the parameters. So the A and the T that were underlying the Hall-Littlewood model need to be taken sufficiently small, and only the 2-point convergence is established. Now, after the appearance of this result, there were two major developments, and these are the papers by Castel and Sarkar that establish a similar type of statement, but with arbitrarily many points for different models. So they work with the ASEP. And there's also the paper by Ball and Farag from last year that shows kind of multi-point convergence for polymer models. So they work with different types of models, and also the techniques are completely different. So they rely on somehow soft techniques, whereas here, this type of result is derived by studying exact formulas. So the methods are different, and also the models that are being considered are different. So I have one slide that says something about that convergence, but maybe I should skip it. So let's just skip it and go to summary. So what I try to convey in this talk is that line ensembles are fundamental objects. So they naturally arise in various types of probabilistic systems of avoiding random walkers, in tiling models, in polymer models, in various types of growth models. So understanding their scaling limit is a hard question, but it's an important one. So if you believe in establishing KPZ universality for random systems, this is what it means to establish it for line ensembles. And even so the techniques that worked in the determinantal point processes fail to be extendable to other settings, but there is now some sort of a framework that, at least for Hall-Littlewood processes and also for low gamma polymers, shows some promise that we can do it, and maybe we can extend it further beyond this. So I think that's all I wanted to say. So thank you very much for the attention.
So questions for Evgeni?
Yeah, I have a question. Hi, can you hear me?
Yes, go ahead.
Yeah. So for your result, like if you are given the law of the first lie plus the Gibbs property, then the whole line ensemble is unique. Like usually, like for every line ensemble, the case line, the fluctuation is roughly 1 over k to the 1/3, right? Fluctuation gets smaller and smaller. So can your proof see this kind of phenomenon?
Oh, no. So as I said, the proof is very much non-constructive. So one thing that would be nice, but again, the method of the proof doesn't allow it, is if you gave me a formula for the top curve, can you get a formula for the second one? So that would be, the ideal type of situation, for the lower ones. A more relaxed question is the one that you're asking, that if you gave me some, maybe even perfect information for the top curve, can I get, sorry?
Oh, like just for the bound for the fluctuation.
Yeah, can you get some, well, you're basically asking, can you get estimates on the variance, for example, or something like that for the lower ones. And right, so the proof is a slick one. It's not a constructive one, and it doesn't really, give you any either qualitative or quantitative information for the other curves. So it's kind of a uniqueness statement. But it's a good question. I haven't really thought about it, and it seems really hard. But maybe something can be done in this direction. Good question.
Yeah, like when I think about this line ensemble, we always worry like the bottom one, it will go crazy. I just wonder if there's some control on the top one can give some information for the bottom one.
Well, that's yeah. I mean, that's a big problem if you prove tightness. You always worry about the kth curve, or the k plus first curve if you want to show the top k's are okay. So you always need to worry about the behavior of the bottom one. But yeah, it's not clear how to do it. But again, I haven't really thought about it as well.
Thank you.
Other questions?
So I guess I have kind of a question. You have this framework that seems kind of, I mean, it seems kind of soft, except for maybe the second point. But I mean, do you think that this could be used for models that don't have exact formulas?
Well, ultimately, that's the goal, right? So we're right. So as you mentioned, this first point is, the analog for Donsker's theorem is to kind of say that, let's say you want to prove something converges to Brownian motion. Then kind of a sensible thing to do is to maybe show that any subsequential limit has independent and stationary increments. So that's the kind of thing that you're trying to model here. Now this second point is, I don't know, at some point I thought that maybe one can try to reduce it to just one point, it's Tracy Whittam, but I could not make it to work. But I think that's what we should try to do. If that's the goal. So the idea here is that that was the goal. We fell short of it, and so this is what we can do. But with time, who knows? Maybe one can come up with something ridiculously clever. I mean, there's kind of big conjectures in the direction of classifying the area line ensemble by some kind of soft conditions, and most of that is very much in the air. But all of these things are kind of related. It's kind of classifying Gibbsian line ensembles and understanding kind of how much information do you really need to pinpoint it is something that keeps me up at night. Not always.
Do you know? I mean, are there kind of examples of things where if the top curve is something really wrong, then it would not be a area line ensemble?
So that's actually it's a hard question. So, well, okay, let me rephrase the question. What I think you're asking, and you can correct me if I'm wrong, is that if you gave me a curve, can I determine whether there might exist a line ensemble that has it, or are there kind of classes of curves that very obviously are not the top curve of a line ensemble? Is that the question?
Because it wouldn't be right, because if it, yeah, right,
if,
yeah,
if it's not equal to the, if
yeah,
it's
if
not
it is equal,
exactly
then it has to
equal,
be
that's
that.
the,
Okay, so,
yeah,
yeah,
that's the classification. But what is I think a good question is, if you gave me some continuous function, you ask me, does it belong to a Gibbsian line ensemble? That is very hard. It's that one I have no idea how you would even approach such a question. but again, this really goes towards, classifying the space of Gibbsian line ensembles, right? So that you know what's in and what isn't, so that if you give me something, I can tell you, oh, there is something. But even kind of simple rules of thumb, like, okay, a simple rule of thumb is if the top curve does not have total variation distance that is proportional to the length, then it cannot be, because, things are absolutely continuous with respect to Brownian motion. So anything that, if your curve is not absolutely continuous with respect to Brownian motion, obviously it cannot work. But anything beyond kind of the obvious, is hard to use as a evidence of either for or against.
Other questions? Okay, let's thank Evgeni again for the great talk.
Thank you.